In the upcoming videos, let's talk about paneling, which is very common in building envelopes. We will first try a simple paneling example, as you can see from my Rhino screen, to demonstrate the key concepts of paneling. There are three steps in paneling. First, you build the panel module, then build the grid. The last step is to populate the panel module onto the grid. If you model the panel module correctly, it should automatically adapt to the size of the grid cells. Let's start from an empty canvas. Place a point data holder on the canvas. Copy and paste the battery 3 times, so there are 4 in total. Place the batteries to form a quadrilateral shape. For each battery, reference a point in your Rhino viewport. Make sure that the mapping is consistent between each battery and the point in your Rhino viewport, meaning that the bottom left battery is referring to the bottom left point, the top left battery is referring to the top left point, and so on. This is not required for Grasshopper, but it makes your brain easier to process the data. Place a polyline component on the canvas. Hold the Shift key to connect all 4 points to the vertices input in clockwise order, starting from the bottom left, then top left, then top right, and finally bottom right. Right-click on the C input and set Boolean to true so you get a closed polyline. Make sure that the points form a convex shape. This is also not required for Grasshopper, but it makes your brain easier. Place an average component on the canvas and hold the Shift key to connect all 4 points. The order does not matter. The average battery returns the center point of the polyline. If your shape is concave, the center point could be outside of the polyline. Let's draw a circle using the average point as the center of the circle. Set the radius to 1 less than 5.00, which is 1 to 5. Under the Surface tab, place the boundary surface component on the canvas. Connect the polyline to the edge input. Hold the Shift key to connect the circle to the edges input. This creates a circular hole in the quadrilateral panel. If the circle is larger than the boundary of the polyline, it no longer creates a hole. Now, our parametric panel module is complete. Let's create a grid. Under the Vector tab, place a rectangular grid on the canvas. Set the size of the grid to arbitrary values. The cells output contains rectangular cells laid in a 5x5 2D array. Let's simplify and graft the C output to access each individual rectangle. Under the Curve tab, place a control points battery on the canvas. Connect C to C. The P output contains the vertices of the 36 rectangles. Since there is an extra 0 in the tree structure, let's simplify the output. Search BAM and select the Explode Tree component. Connect the points output to the data input to investigate the first rectangle as an example. You can see that there are 5 points for each rectangle, where the last point is the same as the first point by reading the coordinates. So for the panel, we only need the first 4 points. For our convenience later, use a data battery and connect the first point to it. Let's use the list item component and connect it to the data battery to access the first point. Place a panel and set the index to 0. Copy and paste the batteries and place the batteries to form a quadrilateral shape. Change the index values to access the other 3 points. Make sure that the location of the battery is correctly mapped to the location of the points in your Rhino viewport. Bottom left battery is referring to the bottom left point, top left to top left, and so on. Now the grid is set up. Let's move the panel module definition behind the grid definition. Let's name the 4 points A, B, C, and D, and make sure they are in clockwise direction. Let's also call these points A, B, C, and D, and double check that it turns clockwise. You can name them in counterclockwise order, but you just have to make sure both of them are consistent. Connect A to A, B to B, C to C, and D to D. You can see that the panel is on our first rectangular cell. To populate the panel module to the entire grid, use the points for all of the cells instead of the first cell. Now you can see that the panel is populated to the entire grid. You can adjust the radius of the circle to test it. The panel malfunctions when the diameter of the circle is larger than the size of the grid. Let's limit the size of the circle to 80% of the grid size. Place a slider between 0 and 1.00 on the canvas. Use a multiplication battery for the slider and the x dimension of the grid. Let's also multiply it by 80%, which is 0.8. Because we need to set the radius of the circle, not the diameter, we need to multiply it by another 0.5, or merge these two values to 0.4. Replace the diameter of the circle. Now the circular void is always inside the rectangle. But if we make the y dimension of the grid smaller than the x dimension, the definition malfunctions again. We can use an expression battery to choose the smaller one of the two values. If x is less than y, use x. Otherwise, use y. Replace the existing connection. Now, regardless of the x-y dimensions, the circular void will always be inside the rectangles at a maximum of 80% of the smaller dimension.